There is a welder qualification test that has to be taken if you use steel backing. There's another welder qualification test that must be taken if you use ceramic. If you change from ceramic to copper, you take another welder qualification test. So in the testing area, the welder must prove his or her capabilities to weld with these various materials. The welding procedures need to reflect this, and if the welding procedure uses other than steel backing, it needs to be qualified by test. So we're leaving the options open to the contractor, but putting teeth into it to make sure that both the procedure has been demonstrated to be satisfactory and that the welder has demonstrated their capabilities to weld on these kinds of materials. Let's talk about single versus double-sided joints. In general, we use steel backing if we have a single-sided joint. Now that's the pre-qualified joint details, and there's one or two exceptions where we weld from one side without steel backing, but most of the time, certainly when we get to heavier material, our pre-qualified joint details use steel backing. Copper and ceramic are not pre-qualified. Only the use of steel backing is pre-qualified. When we go to double-sided joints, we always have a back gouging operation with our pre-qualified procedures. So you put in the root pass and weld up one side or a portion of that one side, flip the plate over, and then you grind into that previous bead or air arc gouge into that previous bead until you know you're into sound weld metal, and then the second side is welded up. So this is showing that the root pass from the opposite side has been removed so that I know I have sound weld metal. A common process used, I've previewed this to you already, air arc gouging. With air arc gouging, we use the same kind of welding equipment that we'd use for welding, but we have a different kind of torch. Instead of a metallic electrode, we have a copper-coated carbon electrode. The electrical power flows through that carbon electrode. In the torch are a couple of ports through which compressed air is passed. So you light the torch, you put on the compressed air, the torch liquefies the metal, the compressed air blows it away. And that shower of sparks there is the metal being blown away. So that's the process called air arc gouging. After we gouge the root, whichever method we use, we weld up the joint. We've been under the heading of CJP Groove Welds. Now let's transition into PJP Groove Welds. Here's an example of a single-sided PJP and a double-sided PJP. PJPs in butt joints, corner joints, and T-joints. Again, terminology associated with PJPs, the included angle. Now we introduce the term depth of preparation. Some of you know that when you detail the shop drawings, this is dimension S for the depth of preparation. We'll come back to that subject. Then there is the root face dimension. Sometimes welders call that the land dimension. Technically, we should call it root face dimension. It's the portion that's not expected to be fused. The gap between the two is the root opening. I've shown this with zero root opening or near zero root opening. We may have a deliberate gap in there as well. We weld up that joint, and once again we have the heat affected zone just like we had with our complete joint penetration groove weld. We get no credit for the reinforcement left over on the cap of the weld. The throat of the weld is defined as the different distance from this upper surface down to the fused root region. So the throat in these welds is by definition less than the thickness of the plate. That means somebody, namely the engineer, needs to determine what the throat dimension should be. The throat dimension is going to depend upon the load transferred across the connection. The calculations for the capacity of PJP Groove Welds are very much like fillet welds, but instead of identifying the leg size, we're going to identify the throat dimension, and we'll review that a little bit later on. With PJP Groove Welds, we have both the E dimension and the S dimension to contend with. What are those? S, as I mentioned, is the depth of bevel that the shop applies to the joint. Now the included angle is typically identified as alpha or A, and then we have the depth of the bevel S. because it's hard for me to remember all this stuff, I call S the shop's dimension. That's what the shop's going to put on the steel. If the included angle alpha is large, and if we get fusion all the way to the root of the joint, the S dimension and the E dimension are the same. What's E? E stands for effective throat. Effective throat. I call that the engineer's dimension. S for shop, E for engineer. E is the effective throat. That's what we can rely on to transfer our loads. Now, it's possible that I could reduce the included angle alpha and save some weld metal. If I reduce alpha far enough, I may not get fusion all the way to the root of the weld. Under these conditions, S is not equal to E. E would be the effective throat that goes down to the depth of fusion, but S and E are not the same. You say, well, I don't want that. I want fusion all the way to the root. Well, let's think about that for just a moment. As long as you have the throat dimension you're looking for, do you really care about whether you have penetration all the way to the root? You see, it's going to be the effective throat E that resists whatever loads are applied. You're not going to get any transverse stress through this area, and you're not going to get it up here either. And so whether or not we get fusion to the root's not critical. The issue is whether we get the effective throat that we're looking for. Now, this has already been handled in AISC and in AWS. Table J2.1 spells out the E dimension and the S dimension for different processes and different kinds of joints and different positions. So to take a couple of examples in here, let's use shielded metal arc. No matter what position we're welding in, if we have a V groove with a 60-degree included angle, then the E dimension, effective throat, is equal to the S dimension, depth of preparation. But if we take that same process, shielded metal arc, regardless of welding position, and we use a 45-degree bevel, then the effective throat E that we get is equal to the depth of bevel, S, minus 1/8 of an inch. And if you go through the table, you'll find that there's actually ranges on these angles. And if you have the larger angles, E is equal to S. If you have smaller angles down to 45 degrees, you subtract 1/8 of an inch off of S. And less than 45 degrees isn't permitted because we can't reliably get fusion to the root. So the way the codes have been set up is the engineer specifies the E dimension and leaves it up to the shop to decide what the S dimension should be. Because you may not know what welding process they're going to use, and you don't know whether they want to bevel it at 45 degree or 60 degree or something in between. And who cares as long as the engineer gets the effective throat E that's required. So we leave it up to the shop to determine the S dimension. And in something I'm going to describe later on, we can use matching, or in this case, undermatching weld metal. And we also have in the code minimum size PJP Groove Welds, and those show up in table J2.3. And these are minimum sizes that are required regardless of the load transferred through the connection. Please don't take these minimum sizes to mean anything in terms of your design of the connection. This does not say that typically for loads transferred through the joint, this is the size of weld you need. You can't predict that. Rather, this has to do with the practicality of welding and how we make all the codes work together. So, for example, if I have material over 1/4 up to 1/2 inch, regardless of what design loads say, I need to put in a PJP with a minimum throat of 3/16. Now, I want you to all think about 3/16. That's not very much, is it? Not very much. And if I put in a weld, let's say I wanted to put in a weld smaller than 3/16. That's an 8. That's even smaller yet. Do you really want to skate a little 1/8 inch PJP groove weld in there on 1/2 inch material? I don't. You put in a weld that small, it's going to solidify and cool so fast that heat affected zone could be a problem. So to make everything work together, the code say, okay, do your design calculations, specify the throat dimension, come back and double check against table 2.3, make sure you've made it at least that minimum size. The reason it's there is oftentimes what you calculate is actually smaller than this. So you go back and you may have to increase the weld size to meet this minimum requirement. Flare V and flare bevel PJP Groove Welds. Our codes have changed recently in this regard, and so I want you to have the latest information that came out in 2005 in this regard. On our specifically cold-formed tubular members, we're using more and more of those, and they look very, very nice. We put in these flare bevel groove welds, and now we want to know what is the throat associated with these welds. Now, the throat is really a function of the radius, and the radius generally is a function, the radius is a function of the thickness of the material and generally follows the pattern of being 2 times the thickness of the material. And what our code says, and this is an example, it's not always the case, I'll show you what it is. The code relates the throat that we get to the radius. And so in one example, the throat is 5/16 times that radius. Now, I mentioned that the radius is a function of the thickness of the material and generally follows a rough pattern of being 2 times T, but mill practice varies. And you might want to check the radii associated with some of the shapes you're getting if this becomes a critical factor. Now, if your radius is small, then the weld that you put in there is likely to be pretty small, and the throat's going to be small. As the thickness goes up, that radius is going to get larger. And that actually presents a challenge because if we fill it flush, these result in some very, very large welds. And the more welding we get, the more distortion we get, and of course the more cost we get. And so filling flush all the time may not be necessary. Now, these are 2 illustrations of the same vertical plate thickness, different radii associated with the tubes, and the net throats that we're going to get from the 2. And I think it becomes pretty apparent, particularly if I say these are back-to-back, that you wouldn't want that kind of detail, right? You don't need that volume of welding in all cases. So now we have provisions in the AISC specification for underfilling the joint. And in this case, you specify the thickness of the throat that you need, and the actual means by which this is implemented is you measure the unwelded portion off of the face. Now, this reduces some cost, reduces some distortion, and unless there's some kind of aesthetic requirement that says you fill it, you don't have to. If you do have one of those requirements you have to fill it, there's other materials like Bondo that are better than weld metal to fill those things out. Yes, sir. There was a big debate in the committees as to whether or not we should be measuring this face width or measuring this depth. And we ended up with measuring depth. So the way I see it is somebody's going to be putting a straight edge on here and using a depth indicator or some kind of gauge to find out what that is. And you're looking for a minimum amount of fill. So I would be looking at some kind of gauge to make sure I filled that adequately. So it's not so much a precise dimension I need to make. I need to just make sure I have the root totally filled. I mean, filled to that minimum point. Okay, so now here's an application where perhaps you don't need that much weld in there, and we're able to reduce it. Same thing here. You may not need that much. That gives you some severe distortion at times, and so we can go to underfilling it in certain applications, measuring that dimension, and taking advantage of it. Table J 2.2. Yes, sir. Would you ask that again, sir?
AIC, they will tell you that when you fill up flare bevel groove weld level, then and then only you can use your throat equal to 5/16 R. So if you fill up partially, what kind of calculation you will make?
I'll answer your question in a moment, okay? We'll get to that. Table J2.2 gives us the resultant throat dimension as a function of the weld type when we fillet flush. This is the old table that preceded the 2005 code. Based upon research that was done by Dr. Jeff Packer at University of Toronto, this has been modified. This is the new 2.5 table. The welding process is now a variable. If we use shielded metal arc or self-shielded flux core with flare bevel, fillet flush, we get 5/16 R. If it's a flare V, we get 5/8 R. With gas metal arc, gas shielded flux core, because these exhibit more penetration in that type of joint, notice we get twice as much throat if we fillet flush. So here we're at 5/8 R and 3/4 R, and there we have the values for submerged arc. That's if we fillet flush. If we don't fillet, we have an X dimension. Take this value, assume I did fillet, subtract off the X dimension that you're not going to fill, and that's what you would use for the throat. If I combine, oh, this is the same table from AWS. We got coordinated this time, and they're both the same. If I combine the general trend that the radius is twice the thickness of the material, then I can combine those two and look at the throat that again is a function of the material. And what's very nice here, as I show in the yellow, these are all the joint details now that give me full capacity that matches T. So here I have actually 5/4 T, 5/4 T, 3/2 T, and down here 1 T. So now I'm developing the full capacity of the connected material with those joint details in those processes. We'll go through fillet welds and then we'll take our break. Fillet welds generally applied to T-joints. They don't have to be in T-joints. Again, like our other welds, they have some terminology. Here we introduce the leg size. In the U.S., we specify fillet welds by the leg size, certainly when we're in 90-degree T-joints. What controls the performance of a fillet weld is the throat dimension. The throat dimension is assumed to be the least dimension from the root of the weld out to the face of the largest diagrammatic cross triangle that can be put in the cross section. Once again, we don't get design credit for the material that's in the reinforcement region. Unless we're deliberately taking advantage of penetration, we don't get any credit for that beyond the root of the joint. We'll talk about that later. Other terms associated with the weld, fillet welds: toes, where the weld blends into the base material; face, where the reinforcements are located; root, down at the apex of the joint. Fillet welds are applied to T and quarter joints and in lap joints. So these are the three joint details to which fillet welds could be applied. In a corner joint, they can be applied to the inside corner. Someone needs to specify the leg dimension, so we need to calculate what that is. Someone needs to specify the length of the weld. They need not be full length of the joint. They could be intermittent. And for these welds, again, it's something we're going to discuss. We can use matching or undermatching weld metal strength. Just as we had minimum PJP Groove Weld sizes, table J2.4 gives us minimum fillet weld sizes. Again, it has nothing to do with design. The concern, rather, is for the practicality of welding and to give us ample heat input to resist cracking. What's very important is that the minimum fillet weld size is often the controlling dimension when we do our weld calculations. So you go through and you make the calculations, the required weld size, and if it's a full-length joint, you often find that what you calculate is smaller than the minimum prescribed size as you see in table J2.4. So here's the example of that table out of the code. out of the specification. AWS has a similar table, and they match up. Now, AWS has footnotes to the table that also add some explanation to the function of this, and I cover those later on, so I'll get back to those in just a moment. We also have maximum fillet weld size requirements. Those show up in J2.2b. Unfortunately, these provisions are subject to a much misapplication. And so I want you to understand the proper intent. These words continue to be tweaked to hopefully get us closer and closer to the proper application. So let's read what J2.2b says. The maximum size of the fillet weld of connected parts shall be along the edges of material less than 1/4 inch thick, not greater than the thickness of the material, along the edges of materials 1/4 inch or more in thickness, not greater than the thickness of the material minus 1/16 of an inch, unless the weld is specifically designated in the drawings to be built out to obtain the full throat thickness. Now this is associated with lap joints. And here's the lap joint where the leg size is equal to the thickness of the material. Years ago, welders learned that if they directed the arc to the corner of the steel and kind of melted away that corner and flowed the metal down, when the inspector showed up, it sure looked like a weld was made the full size. But the throat wasn't what people expected it to be. Because whereas the designer was expecting this throat, what they were actually getting was that throat. So to preclude that practice, this maximum weld size provision was implemented. And it required on heavier material that 1/16 of an inch be left behind, so we know that the corner is there and hasn't been melted away. Now this has resulted in all kinds of problems. About once a year, I get a call from an inspector, and the inspector says somebody has put in welds larger than necessary because they made full-sized welds on these corner joints, and they're objecting to my corrective action. Well, what, sir, is your corrective action? I'm having them grind away 1/16 of the weld, the full length. I usually say, well, that'll make it a whole lot stronger. And then you stop and think and say, well, it complies then. Yeah, it complies, but that's kind of a stupid corrective action. He said, well, I want to teach the welder a lesson. Well, there's probably other ways to do that, too. In any event, if that's a mistake, if we know the edge is there for the rest of the weld and only a portion is melted away, we're not concerned about that. So it's good to understand the background behind that. Now, why does this only apply for thicker material? Because for thinner material, the problem is melting through the whole thing. You can't just melt away the top edge and not melt through the whole cross-section. So it's applied to thicker material. I said it's for lap joints. If you read the wording, it now says along the edge. And this would be another example where you could weld along the edge, right? And this is another place where somebody could abuse that corner and melt it away. So the code now says along the edge. It used to say on lap joints, and now it says along the edge, so it's going to capture this one. Now here's another abuse. That minimum fillet weld size does not apply to this situation at all, does it? This is a T-joint, and you're never welding on an edge. There's no edge involved. For tubular members going down to base plates, it's routinely required for you to put in a fillet weld that's larger than the thickness of the tube in order to get a throat dimension required to resist the load. And I don't know how many times I've gotten a call from designers who say, my wall thickness on my tube is 3/8 and I need a fillet weld, and the fillet weld needs to be 3/8 leg size, and the code says it has to be 1/16 of an inch less. How do I handle that? It doesn't apply to this particular situation. Here's how the code, as AIC specification, deals with the issue in the commentary, which is pretty complete and explains the same thing. Fillet welds are not always in 90-degree joints. It could be in skewed joints. And we might call this a skewed T-joint. Some people call them skewed fillet welds. And you need to be careful when you get into skewed T-joints. Part of the reason is you need to look at how the preparation is applied to the end of that member. Now this is a 90-degree cut on the skewed member, so that the angle of the skew becomes the angle of this gap down in the root. There's nothing wrong with that, but we also need to realize that there are some implications behind that. It's going to be more costly. It's not the routine practice, but that surface could be cut with an angle, a bevel angle, that's the same as a skew, so when the two are brought in contact, there's no gap between the two. Now, the weld detailing that's applied makes a difference depending on that root condition. And if you have a gap on one side, notice that the weld throat is not going to be represented by what you look at of the external fillet weld, but you need to subtract from the leg size the amount of that gap, because your throat dimension is going to be least dimension from the face of the weld to where that root starts. And if on a job somebody's measuring this total dimension and thinking that's the throat, you're getting a smaller weld than you think. AWS has fairly lengthy rules about this. D1.1, 2.2.4, weld size and length. For fillet welds and skewed T-joints, the following shall be provided in the contract documents, typically what the engineer is providing. For fillet welds between parts with surfaces meeting an angle between 80 and 100 degrees, contract documents shall specify the fillet weld leg size. So if you're between 80 and 100, you specify the leg size. If we continue in D1.1, it says welds between parts with surfaces meeting an angle less than 80 or greater than 100, the contract documents specify the effective throat. So if you're less than 80, greater than 100, instead of specifying the leg size, we now go to the throat dimension. Now, because this group's primarily engineers, I talked about what's in contract documents. There are other provisions in there of what the contractor is supposed to put on shop drawings. And so we didn't cover those, but those are also contained therein. Let's cover this last topic on fillet welds. I may not be done with fillet welds. We'll get fillet weld terminations in, and then we'll take our break. The termination provisions contained in J2.2b and in AWS Section 2, and includes the following. End returns and holdbacks for fillet welds, if required by design, shall be indicated on the contract documents. So what is an end return? In this case, the bracket is showing an end return. What is a holdback dimension? That's where we deliberately don't want the weld to continue to the end. If we look at the general condition, it says fillet weld terminations may extend to the ends. And what is that? Well, that's where the fillet weld goes all the way to the end. But the provision also says, or they may be stopped short. What is stopping short? They're stopping short of the ends. Or they may have end returns. There's the end return. And that says we can have any of those except as limited by the following cases. So then we have the exceptions. In lap joints where one part extends beyond the edge or side of a part subjected to calculated tensile stress, fillet welds shall terminate not less than the size of the weld from the start of the extension. So in this particular situation, we have a required holdback dimension that needs to be identified. Now, most of these requirements have to do with workmanship or flexibility of the connection. And the problem with carrying this weld all the way out to the edge is that when you weld into toward an edge, there's not the uniform conduction of heat around, and you tend to undercut the edge. And so that's a workmanship concern. But there can be flexibility concerns associated with that, where we don't want that rigid connection going all the way to the end as well. Maximum end return length. Welded connections shall be arranged to allow the flexibility assumed in the connection of the design, design. If the outstanding legs of the connection base metal are attached with end return welds, the length of the weld should not exceed 4 times the nominal size of the weld. And then we have a figure, and this is an example of a maximum end return size, because there's some flexibility at that angle that needs to be accommodated. Transverse stiffeners, well, we have some minimum holdback dimensions for those, and the holdback dimension of a stiffener, not a transverse connection plate, that's the flange, but for a stiffener, that is between 4 and 6 times the thickness of the web. This is allowed for a little flexibility, primarily in shipping. You carry that weld all the way out to the edge, there can be cracking at the termination of that fillet. On the opposite sides of a common plane, fillet welds are to be interrupted. Here's the illustration of that one. A common plane in between here, and this fillet weld's interrupted here so you don't weld all the way around the corner. And then some of you are going to hot dip galvanize things at times, and you will want to violate some of these requirements because you're going to want to weld all the way around things, or you're going to paint them up, and then you're going to want to violate these. And so you need to consider the engineering behind this, the workmanship behind this, and make sure that when you do have continuous welds that violate this, you're going to get the performance you're looking for. All right, our next area is going to now be comparing fillet welds and PJPs. So now is a good time for a break. And let's see if we can all be back here at, let's try for 5 after 10. How's that, Steve? 5 after 10.